we try to solve some problems on various rigid pavement stresses. And these problems have been taken from the book. The first problem is about to calculate the curling stresses on a concrete slab that has 25 feet by 12 feet and have an 8-inch thickness. Uh, it have uh, it is subjected to a daytime temperature, and the difference in temperature is 24 degree Fahrenheit with a temperature gradient of 3 degree feet per inch. Assume the slab is resting on the foundation with a 200 psi over inch modulus of subgrade reaction. So for us, we have the data as Lx is equal to 25 feet, and we have to convert it in inches. That's why we have multiplied by 12. So length in x direction and length y direction. We know the depth at 8 inch and difference in temperature is 24 inches, sorry, 24 degrees centigrade. And even if it is not given, what we do, sorry, this is 3 degree Fahrenheit per inch. So if for instance, if this on a statement doesn't say anything in the differential temperature, but it says the temperature gradient is 3 degree. And if for instance, if the slab is 10 inches, so this will not be 24, then that will be 10, 3 into 10 is 30 inches. So that's, this is how 24 has been calculated. Or in other words, if you have been given, say, 30 degree Fahrenheit difference, you can easily, and you have 10-inch slab, so we can easily say that there is a 3 degree gradient. Now, what we have done here is make a simple Excel sheet, and we have to calculate 4 parameters. First, we have to calculate the radius of stiffness. For that, we have a formula that has been given to us. It's 1/4 EH cube over 12, 1 minus nu is the Poisson ratio, times K. From that, K is equal to 200 has been given to us. The Poisson ratio for concrete is 0.15. That's why we have taken the 0.15. And the depth of the slab was 8 inches. That is known as H here. And E is 4 million psi. So the tips from that, we have calculated the radius of stiffness is 30.57 inch. This radius of relative stiffness will be used as an input to calculate the factor, the shape factor Cx and Cy. And this is for that we calculate the Cx and Cy from Bradbury chart that is given in the book as well, and we will show that chart here as well. In order to read that Bradbury chart, we have to calculate Lx over radius of stiffness and Ly. So since Lx, we already know that Lx was 300. So we have divided 300 by 30.57. And Ly was 144. And 144 divided by 30.57, we get that Ly over L. And from that, what we have known that this is the chart. So when our Lx over Ly was, we say Lx is 9.81. So what we do, we come to this graph, Bradbury chart, and we have drawn a perpendicular somewhere here, and we estimate that we feel that this is 9.8, and this can be an approximation as well. So we get Cx is equal to 1.09, and similarly, we had Cy as 0.61. That's why around, Ly over L was 4.71. That's why we have calculated this one and we found Cy is equal to 0.5. I'm sorry, I think there is some mistake in it, but actually this is the way. Once we know this value, our third step is to calculate maximum stress in the interior of the slab, and this also has been given uh, in the equations that are ready there in the book. So we have, for that we have to know C1 and C2, elasticity modulus, alpha, delta T, the Poisson ratio. Cx is equal to 1.09, Cxy is equal to 0.61, E is 4 in million, delta T is 24, and alpha is 5 into 10 power minus 6. So that's how we calculate sigma x and sigma y using this formula. Now, if you want to know where is, what is, because we have to calculate stress in three parts. Actually, this problem required this stress in the interior of the slab and the edge of the slab. So for that, for edge of the slab, we need to use this formula, and from that we can get sigma x equal to 262 psi, and if you can also calculate sigma y as well, which is not forget, unfortunately not calculated. So this is, simple way of calculating the stress. Just make these 4 columns, and this will help you in analyzing the problem in a very simple manner. So that's it for the first problem. We'll continue with the other problem as well. Till then,